This is my fifth video lesson for Unit 7. In this lesson, we'll be determining the phase of elements and solving calorimetry problems. Go to page 24 in the class packet. Determining the phase of elements should be reviewed from Unit 1. We will be using a heating curve along with table S to determine the phase of elements. Motivation. Which group on the periodic table has a solid element, a liquid element, and a gas element at STP? If we use table S, that will be group 17. The solid element will be iodine, the liquid element will be bromine, and the gas element will be fluorine. We will be reviewing how to use table S to determine the phase in this lesson. Learning target. At the end of the lesson, I'll be able to determine the phases of all elements at any temperature and solve calorimetry problems. Homework will be number 5, will be a Junipod. There'll be a quiz Junipod on PowerPoints 4 and 5. To figure out the phase of element at any temperature, we have to use the melting and boiling point on table S. If the temperature given is less than the melting point, then the element is a solid. If the temperature is between the melting and boiling point, then it's a liquid. If the temperature is greater than the boiling point, then the substance is a gas. So we'll be using a heating curve to help you visualize this. Example 1. At STP, what is the phase of hydrogen? The first step is to look up the melting and boiling point of hydrogen. If we look on table S, the melting point is 14 Kelvin and the boiling point is 20 Kelvin. We're going to write it on this heating curve. The next step is to determine the temperature at STP. If we look on table A on your reference table, STP is 273 Kelvin. 273 is much greater than 20 Kelvin. So if you were to place it on this heating curve, it will be above the boiling point. So at STP, hydrogen is a gas. Example 2, at STP, what is the phase of lithium? The first step is to look up the melting and boiling point of lithium. It is 454 Kelvin, and the boiling point is 1615 Kelvin. At STP, it is 273 Kelvin. On this heating curve, that will be less than the melting point. So lithium is a solid at STP. Try to do the rest of the practice on your own. Pause the video and resume once completed. Here are the answers. Calorimetry is the process of measuring the amount of heat released or absorbed in a heat transfer or in a chemical reaction, endothermic or exothermic. Here's a setup of this type of reaction. Usually you have an insulated container and your reaction or heat transfer occurs inside a container. The temperature change is measured using a thermometer and the amount of heat released or absorbed is calculated using the heat equations on table T. Heat capacity is the amount of heat to raise a substance temperature by 1 degree. The units of heat capacity is joules over Kelvin or joules over Celsius. The 4 scenarios regarding calorimetry, the first one is finding the specific heat of an unknown substance. The second one is finding the heat capacity. The third one is finding the final temperature after mixing or other variables. The last one is determining the energy lost or gained by a substance. Here is a typical calorimetry experiment. Let's say you have a cup of water that's insulated. You have 100 grams of water inside the cup that is 35 degrees Celsius. Here's 100 grams of an unknown metal. We're going to heat up the metal to 200 degrees Celsius, and then we're going to drop this unknown metal into the water. So what will happen? The heat from the metal would transfer to the water, so the temperature of the water should increase. So the final temperature of the water is 40 degrees Celsius. Then you can calculate the heat absorbed by the water, or you can calculate the specific heat of the metal. We will be using this equation, minus Q loss is equal to plus Q gain. Q stands for heat. The heat loss is equal to the heat gain because of conservation of energy. In this experiment, the metal is losing energy while the water is gaining the energy. The energy lost by the metal should be equal to the energy gained by the water, assuming no heat loss. Since there's a temperature change in our experiment, Q is equal to mc delta T. We will substitute mc delta T into Q. From the experiment, we know the mass of the metal and the mass of the water. The C of metal is unknown. The C of water is on table B on your reference table. Delta T is T final minus T initial. We know the initial temperature of the metal and the initial temperature of the water. The T final is going to be the same for both the water and the metal because they both reach the same temperature. This is because of thermal equilibrium in a heat transfer. Now we know every single variable besides the C of the metal. We can solve for the specific heat of the unknown metal. If we plug in the variables from the experiment into the equation, the mass of the metal is 100 grams. C we're going to put as X. T final is 40 degrees. T initial is 200 degrees for the metal. For the water, the mass is 100 grams. The C of water is 4.18. The final temperature of the water is also 40, and the T initial is 35. If we solve for X, we get X as 0.13063. The metal is most likely lead. There's a list of these specific heats on page 27 in your packet. So we'll be doing a similar experiment in lab, determining the specific heat of an unknown metal. Question 2. How much energy was absorbed by the water and released by the metal? So we have to use the equation Q equals mc delta T. For water, we know that the mass of the water is 100, the C of water is 4.18, and delta T is 5 degrees. So Q is equal to 2090 joules. For the metal, we're expecting the same amount of energy. We will use Q equals mc delta T. If we plug in the numbers, we get Q is equal to negative 2090 joules. So the metal released 2090 joules. As a reminder, a negative sign means releasing energy. A positive sign means absorbing energy. You can do the rest of the practice questions on your own. The answers are on the PowerPoint. So this concludes the video lesson. Remember to do the Juniper homework and quiz.